Pluto is some distance from the Sun, of course, so the solar is multiple times fainter than it is here on Earth. So, its freezing temperatures lower to around -230 degrees Celsius during the night. In an intensity wave, you could get as high as 170 degrees Celsius. It has an incredibly questionable environment too, welcoming inquisitive minds to an investigation beyond the recognizable domains of our solar system. Consider the possibility that I told you that Pluto, the far-off and mysterious bantam planet, is at last taking its inestimable movement, probably crashing into none other than Neptune, the ice giant. Pluto's defiant nature has been apparent from the beginning, a revolt on the edges of our divine region. Its circle, daringly encountering another planet, challenges the normal requirements of planetary behavior. I mean, that's no kind of lad for a planet, right? From the baffling complexities of Pluto's circle to the raised concerns voiced by astrophysical illuminators like Tyson and Kaku, a ready inquiry hangs within the limitless equilibrium. Will these divine monsters participate in a crash course? Should the convergence of their paths spell unanticipated ramifications for our beloved planet Earth? Today, we set out on a grandiose journey full of uncertainty. While the answers to these divine questions may escape us right now, the potential for an impact of such grandiose volume serves as a clear reminder that the universe is a stage for events both stunning and possibly a bit terrifying. Join us as we dig into the secrets that circle how we'd interpret Pluto and Neptune, examining the possibilities of a heavenly struggle that might reshape the limitless equilibrium of our planetary group. The stage is set, and the unfolding show entices us to witness the confounding dance of the planets amongst other potential space catastrophes. The universe harbors a selection of puzzlers, and among them is the difficult riddle known as the three-body problem. But scientists anticipate other likely upheavals in the divine theater. Despite the fact that a planet crashing into another in space is highly unlikely, it isn't entirely out of the question. Gravitational interactions, as explained by the three-body problem, are one of the forces that affect planetary orbits. An illustration of a space system where gravitational forces produce an occasional pattern called orbital resonances is TRAPPIST-1, which has 7 planets the size of Earth. As time elapses, these patterns could weaken planet orbits, enhancing the probability of crashes. What goes on? Does it exclude any crashes? Despite the fact that systems such as TRAPPIST-1 are very dense, and planets affect one another's courses, especially when they are close, scientists consistently monitor these systems to figure out this. With this information, we can better understand how the planets travel through space. Another obscure yet realized element is rogue planets, which move carelessly in space instead of in orbit around a star. Ejection of planets from star systems can occur due to gravitational tugs or other galactic peculiarities, such as another star's near approach or active instability. In systems with multiple planets, over time, these wandering planets can travel vast distances, possibly reaching areas far from where they originated. It is possible that they'll run into other star systems on their solitary adventure. The possibility of a planet crash increments if such a planet is going to another nearby planet group. In any case, a rogue planet striking another planet head-on would be very unlikely, considering how vast and mostly empty space is. The sparsity of planets in open space and the vastness of interstellar distances work together to deter common crashes. It is already highly unlikely that 2 rogue planets will affect, but the frequency of rogue planets is far lower than that of stars and planets in stable orbits. The star systems involved can become chaotic in the event of a cosmic merger. It is highly unlikely that planets will affect head-on during these massive events due to the vast interstellar distances. The orbits of stars and planets in emerging systems are altered strongly by major regions of energy for the gravitational forces. A planet might become a rogue planet liberated from any star when such a disturbance forces it out into the cold, dark depths of intergalactic space. On the other hand, planets may be ejected from their orbits, crash into other celestial bodies, or even impact their host stars due to these gravitational disturbances. When gas and dust are compressed under extremely high pressure, gravitational collapse can actually cause new celestial bodies to form or possibly start stars to emerge. In our solar system, the late heavy bombardment suggests that around 4 billion years ago, there was a period of increased impacts involving comets and asteroids. This surge in celestial activity is believed to have resulted from gravitational disturbances caused by the outer planets. During this turbulent phase, gas giants like Jupiter and Saturn were undergoing migration, disrupting the orbits of numerous smaller bodies in the Kuiper belt and asteroid belt. As a result, these smaller objects were thrown into eccentric paths, with many advancing into the inner solar system. This influx led to a significant rise in impact on the terrestrial planets, including Earth. While these influences did not involve direct collisions between planets, they illustrate how gravitational interactions can lead to significant shifts in the trajectories of celestial bodies. This upheaval is thought to have played a pivotal role in shaping the surfaces and geological records of planets in our solar system. Moreover, it would have contributed to the distribution of water and organic materials to Earth, influencing the development of our planet over an extended period. As stars go through changes in mass, flows, then portions of planets around them might end up farther and probably cross. This is particularly significant in systems where stars are nearing the end of their life cycle. As a star advances in years and burns its nuclear fuel, it often undergoes significant mass changes, especially during stages like the red giant phase or when it releases material in a planetary nebula. These variations in stellar mass can significantly affect the gravitational balance of the system, causing the orbits of neighboring planets to either move outward or become more compact. This is more likely to occur in multi-star systems where complex gravitational interactions can easily lead to unstable orbits. In such systems, the gravitational forces from multiple stars can interact unpredictably, exacerbating orbital disruption and increasing the chances of orbits converging. This can result in situations where planets could get captured by another star, crash into other celestial bodies, or even get catapulted into interstellar space. Pluto's unique orbit, initially recognized as a clear member of the planetary family, underwent a renaming, eventually being designated as a dwarf planet. Because of its unique orbit, the astronomy community remains enchanted by it and finds it interesting. Despite this change, there is cause to worry as to the closeness of Pluto's track to Neptune's. According to recent figures made by renowned scientists like Neil deGrasse Tyson and Michio Kaku, these scientists are sounding the alarm about a grave hazard to Earth, the probability of an impact between the planets. Pluto is unlike any other planet in our local planetary group, and that is what makes its circle around the Sun so unique. Pluto has not completed a full revolution since its discovery in 1930, and its circle ranges an extended 248 years. The fact that it veers off significantly from the usually spherical circle of the massive planets makes its path extremely abnormal. Further adding to its reputation, Pluto also has a more extreme circle than other planets because its inclination to the ecliptic plane is 17 degrees. Adding unpredictability to Pluto's orbital pattern is the combination of its elliptical shape and inclination. The point at which Pluto's circle runs into Neptune's is an interesting feature. During around 20 years in each circle, Pluto ventures closer to the Sun than Neptune, challenging assumptions based on their respective positions in the local planetary group. This leads to the question, why hasn't an impact between Pluto and Neptune occurred? The explanation lies in the gravitational influences exerted by other planets. The assessment of Pluto's circle began rapidly after its discovery, providing a difficult conundrum for astronomers. Unlike most planets whose circles align especially close to the ecliptic plane, Pluto's unique characteristics include a steep inclination and an elliptical shape. The mystery deepened with the realization that Pluto's circle crosses that of Neptune. The three-body problem, Pluto's circle remains stable amid the complexities, serving as a testament to the intrinsic complexities of celestial mechanics. Understanding the motion and gravitational interactions of three celestial bodies like Pluto, Neptune, and the Sun is called the three-body problem in space. Predicting their trajectories from their initial positions and the effects of gravity on each other is similar. For Pluto, some of the terms that help to solve this astronomical mystery are azimuth libration, scope libration, and the VZK oscillation. According to astrophysicists, azimuth libration is crucial because it keeps planets in their circles. When Pluto crosses Neptune's circle, it is something like 90 degrees distant, which is a critical distance that prevents impacts. According to this definition applied to Pluto and Neptune's scope libration, alluding to the upward movement of a celestial body in its orbit, ensures that when Pluto approaches Neptune or other giant planets, it is positioned generally over their orbital plane, providing an extra layer of protection against crashes. A critical factor in understanding celestial motion is the VZK oscillation, named after three scientists, Van Lee and Kai. They explored the gravitational interactions between three space objects, including Pluto, Neptune, and the Sun. The VZK oscillation figures out why Pluto's orbit around the Sun appears uncommon but remains steady over time despite the apparent irregularity in space. Hidden patterns and rules keep everything in check. These factors together stabilize Pluto's orbit, preventing collisions with Neptune or deviations from its path. The three-body problem allows us to understand how the gravitational pulls of these space objects affect their course. Considering this enhances our understanding of Pluto, our local planetary group, and celestial bodies. Mathematical simulations in the late 1980s revealed that despite stable properties, Pluto's orbit is indeed chaotic, with minor initial deviations leading to large variations over thousands of years. Despite this inherent chaos, Pluto's orbit demonstrates remarkable stability over vast intervals, effectively mitigating expected turbulence. Recent digital simulations have improved our understanding of the complex dynamics, including the impact of large planets like Neptune, Jupiter, and Saturn on Pluto's path across the Sun. Neptune's significant gravitational influence, completing 3 circles for every 2 of Pluto, considerably contributes to the overall stability of Pluto's orbital path. Jupiter's gravity is also significant, albeit less so than Saturn's. Taken together, these observations illustrate that Pluto is in stable and regular motion throughout space. Over billions of years, it is crucial to continuously study and explore these events. Space exploration often reveals the unpredictable behavior of celestial bodies. Pluto's orbit is a classic example of this unpredictable behavior. It illustrates how minor changes in the dwarf planet's location or velocity can profoundly affect its orbital course. Scientists' understanding of Pluto's movement in space is largely due to digital simulations, which mimic the gravitational interactions between Pluto and other planetary bodies like Neptune. These simulations utilize complex mathematical models, allowing astronomers to see how small changes can significantly impact Pluto's course. The case of Pluto provides a vivid illustration of the concept of orbital chaos, demonstrating how the trajectory of a celestial body is highly dependent on its starting point. For centuries, scientists' understanding of Pluto's movement in space has been aided by digital simulations. These models have revealed intriguing insights into the complex dynamics of the dwarf planet's orbit, shedding light on its peculiar behavior and highlighting the intricate interplay of gravitational forces in our solar system. These simulations have also helped scientists understand the potential risks associated with Pluto's orbit, particularly in relation to its proximity to Neptune. While an actual collision between Pluto and Neptune is highly improbable due to gravitational influences from other planets, ongoing research and monitoring are essential to assess any potential threats to Earth and our solar system. In conclusion, Pluto's orbit and its interactions with other celestial bodies present a fascinating and complex puzzle for astronomers. Despite its chaotic nature, Pluto's orbit remains stable over vast timescales, demonstrating the intricate balance of gravitational forces at play in our solar system. Through mathematical simulations and ongoing observation, scientists continue to unravel the mysteries of Pluto's orbit and its implications for the dynamics of our cosmic neighborhood. Exploring the depths of space offers a window into the awe-inspiring complexity of the universe, where celestial bodies like Pluto challenge our understanding and ignite our curiosity. As we journey further into the cosmos, the secrets of Pluto's orbit and its interactions with neighboring planets promise to unveil new insights into the dynamics of our solar system and the broader universe beyond. Pluto's orbit has long fascinated astronomers due to its unique characteristics and its interactions with other celestial bodies, particularly Neptune. Initially classified as the 9th planet in our solar system upon its discovery in 1930, Pluto was later reclassified as a dwarf planet in 2006 by the International Astronomical Union. This reclassification sparked renewed interest in understanding Pluto's orbit and its place in the solar system. One of the most intriguing aspects of Pluto's orbit is its eccentricity and inclination relative to the ecliptic plane. Unlike the orbits of the major planets, which lie relatively close to the ecliptic, Pluto's orbit is highly inclined at an angle of about 17 degrees. This inclination, combined with its elliptical shape, makes Pluto's orbit significantly different from those of the other planets. Furthermore, Pluto's orbit is also unique in its interaction with Neptune. While Neptune is the 8th planet from the Sun, its orbit intersects with that of Pluto periodically. This means that there are times when Pluto's orbit brings it closer to the Sun than Neptune's orbit. Despite this close approach, actual collisions between Pluto and Neptune are highly unlikely due to the complex gravitational interactions between the two bodies and other planets in the solar system. The study of Pluto's orbit has led to the development of mathematical models and simulations to better understand its behavior. These simulations take into account the gravitational influences of the Sun, other planets, and even large asteroids and Kuiper belt objects. Through these models, scientists can predict the future trajectory of Pluto and assess any potential risks associated with its orbit. Recent advancements in computational techniques have allowed for more accurate simulations of Pluto's orbit, revealing its inherent stability despite its chaotic nature. While minor perturbations can lead to significant changes over long periods, Pluto's orbit remains remarkably stable over billions of years. This stability is a testament to the delicate balance of gravitational forces that govern the motion of celestial bodies in our solar system.